This is 4.6, independence and conditional probability. So we talked about mutually exclusive events. Well, if things aren't mutually exclusive, they can be independent. They can also not be independent. They can be neither mutually exclusive nor independent, or they could be mutually exclusive, or they can be independent. So this is a new term, independent events. Two events are independent if the occurrence of one does not affect the probability of the other. So, from previous lessons, we talked about things like drawing cards. Okay, if I draw a card without replacement, and I set it down and draw another card, the probability for that second card has changed, right? Because I have my deck of cards, only has 51 cards now. It doesn't matter what it is, it's changed. So that has changed my probability. So those would not be independent. Okay. Example of an independent events are two very different things. So like the examples where we like spun a spinner and then rolled a die. It doesn't matter what I spin on the spinner. If I roll a die afterward, I still have all the possible outcomes, right? If I flip a coin, it's independent, right? It doesn't matter, I always have two outcomes possible. If I'm rolling a die multiple times, it doesn't matter, I have multiple outcomes. If I'm drawing a card and looking for something with replacement, it's not going to matter, okay? So that's with replacement. Can you have two events that are both mutually exclusive and independent? Well, mutually exclusive says they cannot occur at the same time. Independent says if one happens, it does not affect the probability of the other. So they actually can't be. Think about it. If I have mutually exclusive events, when one of them happens, what happens to the probability of the other? We just said if one happens, the other cannot happen. So that means it changed the probability to 0. So they're definitely dependent. That's the opposite of independent, dependent. So no, mutually exclusive events are dependent because it changes probability. In fact, it changes the probability to 0. Okay, so that's something to take note of. The second word we're going to look at, which is in the title, is conditional probability. So when we talk about independent events, we can look at the conditional probability. The conditional is probability that represents the probability of event A given that event B has occurred. So if they're independent, the probability won't change. If they are dependent, the opposite, if they're dependent, then the probability will change. So this is a new little notation that you want to take note of. How we read this is probability of A, and then this line, it's not absolute value. You reread it in math as, well, in probability as given. So this is, you read this, the probability of A given B. Okay, so example 1, it's the probability of a king given face cards. Okay, so we want to find the probabilities now. So, conditional probability. We have to use the conditional probability to test independence. That's why we're doing this first. This has a given, meaning the thing afterward has already occurred. Event A given event B has occurred. Okay, so I'm looking at the probability of drawing a king given the fact that I have a face card. Okay, what is the probability that this face card I drew is a king? Okay, a lot of people get confused by this, but remember, I'm telling you the given is already happened. That means I'm telling you in my hand is a face card. What is the probability that it is also a king? Okay, so that means I've limited my deck. The given limits your options. We don't have the full deck. We're not dealing with the full deck anymore. I'm telling you in my hand is a face card. Okay, so we only have 12 possibilities, the 12 face cards. 4 of those are a king. So we can simplify, we can divide, whatever you want. It's pretty easy to simplify this one. 4 goes into both, 1/3, done. All right, now what's the probability of ace given red? So once again, I've drawn a card and I'm holding a card and I'm telling you this is a red card given red. This is a red card. So I only have 26. You can kind of think about this as a fraction line, right? The fraction line is telling you what's the red cards. How many red cards? Fraction line, how many face cards? This one, once again, fraction line, how many face cards? And then you have to ask yourself, of those, how many are aces? Well, I have 4 aces in the deck normally, but it's changed. I've told you it's only red, so I don't worry about the 2 black aces. I only have 2 red aces. So it's 2 out of 26, because all I'm thinking about are the red cards. So there's 26 red cards. 2 of those red cards are aces. So once again, I'm just going to simplify real quick and be done instead of dividing, because 2 goes into both pretty easily. And we have 1 over 13. Oh, that's good. There we go. Okay. So probability of ace given face cards. So we're given the face cards again, so that means I have the 12 cards. All right, so think about it. How many of those face cards are aces? Well, none of them. So we get 0. All right, the face cards are Jack, Queen, King. Those aren't aces, so that's it. We're done. Okay, so we could test for independence. The test for independence, so this test is using the conditional probability. It doesn't matter which one. They really mean the same thing. The 2 probabilities don't change. They're equal to each other. Equal means the same. They stay the same. So when we ask the question, are a king and face card independent? So we look at the 2 probabilities. So you look at the probabilities of just a king, and then you look at the probabilities of a king given a face card. Or you can flip them. You could be looking at the probability of a face card and the probability of a face card given a king. It doesn't matter. Okay? So I just like to do the first one and then the second one. Makes it easy. So what is the probability of the king? Normal. So this is a normal deck of cards. 52, 4 kings. We can simplify 1 over 13. 1 over 13. 4 goes into 52 13 times. Okay, next we look at a king given the face cards, right? So don't forget we're given face cards, so we only have the 12 face cards. How many of those are kings? 4. Simplifies to 1/3. Is 1/13 the same as 1/3? No. That means they're not independent. Also known as dependent. So that's what I'm actually going to answer. These are dependent of each other, meaning they change the probability. And if you tested the opposite way, you would find that the probability would change once again. Okay? All right, example 3. Are an ace and a red card independent? So we'll look at probability of ace, just the first one. And then we'll look at the probability of an ace given the fact that I have a red card. Okay, so ace, just in a normal deck of cards, there are 4 aces out of 52, 1 over 13. Ace given red. So now I'm given the red. Remember that changes our bottom number. Only red cards, 26. So I'm only looking at red cards. So how many aces are red? 2, which we can simplify to 1 over 13. Notice those are the same. 1 over 13 and 1 over 13. Those are the same. That means yes. Yes, they are the same. Yes, they are independent. The probability didn't change. If I, oops. Maybe I should spell that right. There we go. If I was given just the red cards or given a full deck of cards, I would have the same probability of drawing an ace. Independent events. Are a 2 and face card independent? Okay, so probability of a 2. Probability of a 2 given the face cards. So 2, this happens to be the same. That's just using simple examples, so it happens to be 1 over 13. It won't always be 1 over 13. I am given only face cards. How many of those face cards are 2? Well, none of them. Did my probability change? Yeah, I did. So are they the same probability? That's the question I should ask. Are they the same probability? No. That means they are not independent, which is called dependent. The opposite of independent is dependent. Everything is either independent or dependent. So this one is dependent. Okay? Because the probability changed. So Then we can use tables. So example 5, find the probabilities using the table. So we're going to have all sorts of probabilities thrown in here with this table. So you want to pay attention to this. All sorts of things. First of all, if they haven't filled out totals, we need to fill out the totals. So I'm going to add across. So total students in AP Calculus, 40. Total students in Statistics, 90. Total students in Advanced Math, 50. And then we can count up how many transfer students total there are. So 30 plus 15 is 45. And we can count up how many non-transfer students there are. So that's 40 plus 70 is 110, plus 25 is 135. And then the grand total, this one, I'm going to even outline it again, because this is the grand total. This is the total number of students we're dealing with, and they should match. This sum should equal this sum. So we don't have to do it once, really. So it's 90 plus 90 is 180. 45 plus 135 is also 180. So that is the same. That's called the grand total. Okay. And that's how many people we are talking to or talking about. So what is the probability? If I took all of my students and I selected one, what is the probability that student would be an AP Calculus student? Well, I have 40 AP Calculus students out of the grand total, because I'm looking at all of the students. And there we have it. And I can simplify. You can write the decimal, fraction, percent. I can see 20 goes into both of these pretty easily, so I would write the fraction. But if you just divide them and get the percent, that's great. Do that. It's up to you. Transfer given AP Calc. Okay, remember that given changes what we're looking at. So we are only looking at AP Calc students. So that's my bottom number. The given, the thing after the line, remember I think of it at the fraction line. It's telling you what to put at the bottom, 40. Okay, but we're only looking at AP Calculus students. I don't even care about the rest of the graph. This is the only thing I'm looking at. How many of these are transfer students? Well, 15 of them. I can see easily 5 goes into both, so it's 3/8. Or you can divide and get your decimal or percent, same thing. Okay, we got another given. So I'm given stat students. So once again, they're giving us only the stat students. So I have the 90 stat students. How many of those students are in advanced math? Well, if they're in stats, they're not in advanced math. So the answer is 0. We don't have any overlap. So that one's 0. Okay. And there's all sorts of questions. We can ask some ors, you can ask ands, you can ask all sorts of things within that table, which we will go over next lesson, actually. And then you have the multiplication rule. I'm not even going to highlight this because you have already been doing this. You didn't know it, but you've already been doing it. When we talk about without replacement, right, we're changing the probabilities as we go. That is what the multiplication rule is telling you. It's saying if you have and, you're multiplying, which we already know. And that it's the probability of A times the probability of B given A, right? That's why we always assume the first one has happened. Given the first one, what's the probability? So we've already been doing this, not even going to go over it. Don't have to worry about it. But if they are independent, you just multiply the two probabilities together because they do not affect each other. All right, so there you go. That's the multiplication rule, which you've actually already been doing. So you can write your 3-sentence summary. We've talked about quite a few things, the independence, the multiplication rule, the table, the conditional probabilities, all of those. 3-sentence summary. There you go.